It feels natural to assume that the more features you feed a model, the smarter it gets. In practice, the opposite is often true. Pile on irrelevant or redundant columns, and you invite noise, overfitting, slower training, and a model nobody can interpret. Frequently, a smaller, carefully chosen handful of features generalizes better than the whole pile. So the real skill is not gathering features. It is deciding which ones to keep. That is feature selection, and there's a right way and a dangerously wrong way to do it. Let's dig in. So how do you actually carry out feature selection? Think of it as a short pipeline that turns a bloated feature set into a lean one. Follow it one stage at a time. Start with every candidate feature you have, the full, messy pile of columns, some genuinely useful, many redundant or pure noise. At this point, you do not yet know which is which, and that is exactly the question the next stage exists to answer. Next, score or search your features using one of three broad approaches. Filter methods rank each feature on its own, using correlation with the target, mutual information, or variance, fast but blind to interactions. Wrapper methods actually train models on different subsets and measure performance, accurate but expensive. Embedded methods fold selection into training itself, like lasso zeroing weak coefficients. Whichever method you use, the payoff is the same. Keep the informative subset and drop the rest, throwing away the columns that only added noise. What survives is a compact set of features that genuinely carry signal about the thing you're trying to predict. Finally, train your model on that leaner feature set, with less noise to distract it. The model tends to generalize better, it trains and predicts faster, and it becomes far easier to explain, which is often just as valuable as the accuracy itself. Why bother selecting at all, rather than just handing the model everything? Here is the contrast, side by side. Throwing in every feature you can find feels safe, but it quietly backfires. Irrelevant and redundant inputs add noise, and as the number of dimensions climbs, the data spreads thin and models overfit, chasing patterns that are not really there. Training slows, prediction slows, and interpretation becomes hopeless. More is very often less. Feature selection keeps only the inputs that actually earn their place. By discarding the dead weight, the model sees a cleaner signal, generalizes more reliably on new data, runs faster, and becomes something a human can reason about and trust. In regulated fields, that interpretability is not a luxury, it is a requirement. Strip it down, and three ideas define feature selection. The core idea is subtraction. You choose a subset of the original features and discard the rest, cutting noise and redundancy so the model can focus on what matters. Crucially, it keeps real, named features, which is what separates it from dimensionality reduction like PCA, where the new axes are blended combinations you can no longer interpret. The second idea is the toolkit. Selection happens through filter methods that score features cheaply, wrapper methods that search subsets by training models, and embedded methods that select during training, such as Lasso's L1 penalty or a tree ensemble's importance scores. Each trades speed against thoroughness. The third idea is the trap that catches everyone. Selection must happen inside cross-validation, using training data only. Peek at the whole data set while choosing features, and you leak information from the test set, quietly overstating performance until reality bites on truly unseen data. All right, let's lock in the essentials. Feature selection chooses a subset of your input features and discards the rest, because more features frequently hurt rather than help a model. The three families are filter methods that score features independently, wrapper methods that search subsets by training models, and embedded methods that select during training, like lasso. It boosts accuracy on noisy wide data, shrinks models for faster deployment, and improves interpretability. And unlike PCA, it keeps the original, meaningful features rather than blending new ones. Above all, run selection inside cross-validation on training data alone, or you leak information and overstate how good your model really is. If keeping the signal and cutting the noise is the kind of thing you enjoy, there's plenty more of it waiting at Standardy.com. Come learn with us.